Okay, so the second lecture is about dynamical system modeling. Yes, sometimes we just say system modeling, or but of course most of the system have dynamic property. So dynamics mean when you have equation, it has the form of differential equation. Differential equation in function of time. That is the key word to say it's dynamic system. So why we do this modeling? So here I give one example. A DC motor in operation. Yeah, let's say you have a DC motor and you need to supply electrical power, and what you can play around is the voltage. So here is the supply voltage with a switch. Initially, the switch is open, so no current flow through here. Then no torque is produced. The motor is at rest. Okay, no motion. And let's call the moment the switch is open is the negative time. So let's negative time from any time in the past until you start to operate the motor. So at instant t equal to 0, you switch on, then the motor start to move, right? It start to move. So if you observe, if you can change the voltage, you give the voltage is like only 3 volts, then the motor rotate. When it's rotate at a constant speed, it rotate at a very low speed, right? Compared to the voltage of 6 volt. You increase to 6 volt, the angular velocity is faster. Okay? And you increase to 12 volts, it can rotate even faster. And what I'm showing here is kind of experiment that start from t equals 0. When t is 0, the motor is at rest. Okay? Then you switch on. Of course, the speed start from 0 until it's stable here. And so this part is called, yeah, I want to explain the terminology from now. This part is called steady state. Okay? And this part is called transient. Transient, I-E-N-T. Okay? Transient. So yeah, it's similar to the word transition. Transition from one state to another state, like that. So something change. Can you can put it that way. So until it has constant velocity, then we call it steady state. Yeah, but steady state doesn't mean it must be constant. Let's say if you have an input voltage, as you can change the input voltage like this, like sine wave. Okay, let's call U here is sine wave, and then you have the motion of the velocity, the angular velocity of the motor. Let's say at the beginning it seems not how to say, yeah. Let's say at the first few seconds or maybe less than a second, uh, the shape of the curve here is not uh, like it is not a repeat. It is not repeat itself like this. So during this time we also call it transient. So during this time we call it steady state because it repeats the same. Okay. It has the same sine wave. And so let's say if we want to control the motor to turn to a certain degree, one either to rotate 90 degree or 40 degree or 30 degree, depends on the purpose with the system. Yeah, if it's robot arm or it's some other flywheel for other purpose, then you need to compute the right voltage, the profile of the voltage in a function of time, right? So you need that. You need to compute it correctly. So how can you do it? That comes to the modeling. You need to know the behavior of the system, whether it's first order differential equation or it's second order differential equation. So the response of the output uh, behaves like what? So you need to know that. Then we need the modeling, and I repeat, the dynamics means the equation is in the form of differential equation. Okay. So in many systems, there can be multi-physics. Multi-physics means it can have electrical part, can have hydraulic part, and can have mechanical part. For instance, here the DC motor here it has electrical part. Yeah, from the supply voltage inside here. Okay, inside here are electrical part. Okay, it has inductor, it has resistor, it has um, back EMF, and then mechanical part, which is the inertia with the flywheel, and if you gearbox, yeah, you need to model the gearbox if you want it with the very detailed modeling. Okay? Yeah, so multi-physics. Um, Here, just want to give a review on modeling on particular components. For example, here the definition of current. Yeah, I will go quickly. Definition of current is the rate change of charge, right? The rate change of charge goes through. Let's say you have you put something like to count the charge. Yeah, you have something here to count the charge. Then the amount of charge passed through this wall per amount of time, it is current, right? So by definition it means you count Q now, and then at a short time data T, you have data Q pass through this wall. Okay. Uh, so from T to T plus data T, you have amount of Q on the right hand side is uh, yeah, from Q to Q plus data Q. Okay, right? Then you compute the rate change of charge with respect to time, which means this minus this divided by this minus this, and put the limit of t approach to zero. Then you get this definition of current, right? Is the time derivative of the charge with respect to time. For the property of resistance means something that some obstacle that does not want the current to flow easily. Okay? So this gray dot represents resistance. If there are more this gray dot, it means the current cannot flow easily. That's why the current is inverse proportional to resistance. Okay, very simple. And there are different uh, type of resistance. It, its appearance also reflect the value of resistance. This one is like kilo ohms high or higher. The scale is kilo ohm. This one is scale on this ohm. This one also. This one as well. Okay. How about capacitor? Capacitor is device that can store amount of charge. Okay. So the plate in parallel, the more charge it can store. So it can store energy, right? So actually the higher, the larger the surface and the closer the two plates put together, it means the more charge it can store. So that's why the amount of charge is proportional to the size, the physical size. And physical size can be lumped into one parameter. It's called capacitance. Sorry, capacitance. So capacitance is huge. It means it can store a lot of charge. And of course, the charge is proportional to the voltage. You put higher voltage, it means uh, you put a stronger electric field here, then it can store more charge. So that's why charge is proportional to physical size and the voltage that you impose to create strong electric field. So therefore, the relationship between current and voltage is like this because current is the time derivative of charge. Then the relationship between current and uh, voltage is like this. Okay, very simple. Huh? Yeah, you take time c time v here. Time derivative c is constant. As I said, engineers like to simplify things to make our life easier, right? Try to make this thing that has constant capacitance. Okay? Then you can easily have a relationship between, linear relationship between current and voltage. For the inductor it can store energy in form of rotating magnetic flux. One the current go through here, current flow here. Yeah, flow here is through this conductor, and then the magnetic flux is created and rotate in the spinning inside here. So the spinning of a magnetic flux is like spinning the flywheel like this. So what you put a load here. You put here is like current. The force is like current. When you impose current, first it no, the force is like voltage. You put the constant voltage, so here you have a constant weight. When you put it first, it doesn't want to move. Because of the flywheel, it resists. The flywheel resists it in a short time. But when it's moving, it can move faster and faster. But when it's move very fast, even though the roll wire here is finished, and then it start to roll in another direction, it bring this one back, right? You can imagine that. And here the same thing, when the magnetic flux was spinning fast enough, and you stop giving the voltage, also you short the circuit, the current still can flow. It's like that. So very simple relationship between voltage and current. Yeah, so voltage here is proportional to the time derivative of current. Okay, if current is strong, magnetic spinning also strong, and the rate change of magnetic flux here with respect to time give voltage. So here's just a table summary of relationship between current and voltage for capacitor. Yeah, you can see here for resistor. Okay, So yeah, you for the um, one parameter that uh, make relationship between current and voltage is called resistance and or conductance. So conductance is inverse of resistance. It means if the resistance is big, it means conductance is small. Conductance means how much it can give the current to flow. Conductance big, it means current flow big. Okay, big current flow. That's why it's inverse of resistance. Okay? It's just a term, right? Okay. And the way you can model for electrical circuit, you use some law, like Kirchhoff current law. You apply on a node, the sum of all the current go into the node are zero, is zero. Right? The sum of all current to the node is zero. And you can apply Kirchhoff voltage law to uh, a loop of electrical circuit. The sum of voltage at each element in the loop must be zero, right? And some system have impedance connect in series, some have impedance connect in parallel. So I think this is a high school formulation. When you have a series connection of impedance, then the total is just the sum of all impedance. If you have impedance connect in parallel, then the total conductance is the sum of each of all conductance, right? It means inverse of resistance. So it's very easy to formulate that. Um, Voltage divider, yeah, this is a fast way to make a model. You have input voltage to here, so voltage here represent here and here. Okay, so if you want to find voltage from here with respect to this, so it's like you have a fraction of the total. The total is you have here with respect to here. Then you have a fraction here. You want to find a fraction here. So it means the fraction of impedance here divided by the total impedance and then times the input voltage, you get the output voltage. It's very easy, okay, to see this way, voltage divider. And then example of OC circuit. Some of you have seen it many times already, so I don't explain in detail or step by step. So I show the whole thing in here. So this is the input voltage, resistor, capacitor, and output voltage here that you want to model. And in here actually I put the switch K in here, and then the switch K here, when it switch to here, it means you supply the voltage V in inside. But if the switch K switch to here, it means you short the circuit. You short the circuit here, it means you give the zero voltage. So you short circuit here, zero voltage, capacitor can discharge. But what if you don't have this? Yeah, sometimes when you make the model, you're very careful with the actual circuit. If you want to build an actual circuit to validate your modeling, and then you forgot this part. When you open the circuit here, it means you cut off the voltage 12 volt, for example. You want to cut off, but you just open it. So when the capacitor never discharge, right? Capacitor discharge and voltage is there, it's still there. And be careful not to touch it. You can get electrical shock. But if you want to make model that after you supply it 12 volt, then you want to supply it 0 volt. If you want to supply 0 volt, you must short them, right? Yeah, you must short here. So it means you switch okay, from here to there in order to short it, so capacitor can discharge, right? And so yeah, to derive this equation, just use a Kirchhoff voltage law and apply the definition relationship between current and charge, and then current and voltage, and put in the Kirchhoff voltage law. Here, you automatically have differential equation to describe it. So yeah, look at here, differential equation is just the form of H dot plus AH is equal BU, which means I think this is wrong, right? Or see here, yeah, it should, or see here, V in, V out. Gee, what happened? How come? Well, from here I can get this one is totally wrong, right? 1 over RC here, and also 1 over RC here. Yeah, and it's very easy to analyze with this model. We say at steady state, the voltage tend to be constant. If output voltage is constant, the derivative will go to zero. It is when it go to zero, it means V out equal to V in. Coefficient 1 over all C is same. Right? Simple analysis. Sometimes you need to use that analysis. Okay. Yeah, so the voltage you here, let's say, is jump from, when the switch is on, voltage input jump from 0 to 1 volt, and then the voltage of the output is like this. Okay, go to 1 like that. So when we approach to the asymptote here, it means go to constant. So the derivative is 0. At steady state is 1 go to 0, so which means V in equal V out. It should be like that. Once at the beginning, the current, because the capacitor has no charge, current can flow a lot. But when the voltage at the output approach to voltage of the input, the current start slowing down and near zero. And when the current is zero, then voltage output must be equal to the voltage input. Okay. So the equation here tells you what happened in here, right? Yeah. For the OR circuit, um, yeah, you can apply first Kirchhoff current law at this node. Okay, current IL equal to the sum of current at the IC and IR. Okay, like this. Yeah. So if direction current into the node, you use plus term. If it's out of the node, you use minus sign like this. So the sum of all current go to the node is zero, right? Then you can have relationship IL and IR, and put all the current, the relationship between current and voltage. Okay, voltage out or VC, like this, V out and VC just same because they are in parallel, and substitute into the voltage law, the Kirchhoff voltage law. Then you can have an equation. Second order equation, very easy to derive. So. And so, what is the behavior of this kind of dynamics equation? Yeah, again, you expect that the voltage of the capacitor here should go approach to the input voltage here, right? First, first the charge is zero. Of course, current flow very fast. Yeah, but maybe not too far because you have inductor here. Right? Inductor resists the current at the initial. That's why you can have this shape, the kind of shape. At the beginning, the inductor doesn't want a current to flow. It's like that. That's why you have this behavior. You have convex. You have convex like this, and then you have concave. No, this one is concave, right? You have concave, yeah, concave, and then convex. You understand the meaning of concave, convex? Yeah, it's yeah, concave like this, right? Maybe and this convex. Anyway, maybe I confuse maybe in another way. Yes. The sweet term. Um, yeah. So when t go to infinity, we all we is expected to approach asymptote, so expect to be constant, which means this one go to zero, this one go to zero, we out must go to v in, approach to v in, like that. And yeah, again, if we input the v in just 3 volt, the voltage of v out will approach to v in when t go to infinity, which is 3 volt. Okay, if v in is 6 volt, then the asymptote for the V out is at symbol as well. So it has this kind of shape, second order. So now modeling tells you if you have all C circuit, you have first order differential equation. If you have all other C circuit, you have second order differential equation. Next part about mechanical element and modeling. A mass, okay. To derive the dynamic equation, you use Newton's second law. Okay? So you have a mass, and you push it by a force F. So it move in the direction h, and it has velocity h dot, and it can have acceleration h double dot. Okay, and from Newton's second law is F equal to ma, which means F equal to m times h double dot. How about the rotation motion? Very similar, but now you change from F to from force to torque. Okay, you change from force to torque, and you change from mass to inertia. This is sometimes we call it torsional inertia. Um, and you change from acceleration to angular acceleration. Okay, and you can oh, sorry, acceleration alpha. Alpha is actually omega dot, right? The derivative of angular velocity. Or you can say it is the second derivative of angle. Okay? So angle is the unit of angle is radian. Then the angular acceleration has the unit of radian per second. Okay. Okay. Next about mechanical elements, like spring. So for the spring, a spring that has a uniform profile. First, without any load, the height is h0. When you put a load on G, yeah, which is force on the spring, and then it drop by h by the amount of displacement h. Okay, and if you put another which is the same as one, okay, one equal to two here, and then it fall down another displacement h, so in 2h. This implies that uh, the displacement is proportional to the force, right? Yeah, proportional to the force. Um, yeah, similar for the rotational spring. How about damper? Yeah, damper, the force is proportional to the velocity. Let's say, yeah, you have a damper, you have a liquid inside. Okay, you have liquid inside like this. So when you have a force pushing down like this, the liquids flow from here to here. Okay, so the smaller you have this tube, the larger the viscous coefficient. Okay, yeah. So in here, by definition, the force is proportional to the velocity. Okay, force proportional to velocity. Okay, you put more force, it can fall faster, like that. And the C depends on the size of this tube. Yeah, this is called damper. Um, yeah, I have table describe all this relationship between force and yeah, force and velocity, force and displacement. Yeah. So you can have the lecture now and read it again later. Yeah. So this lecture is very quick because it's just a review of a lot of physics that you have learned in foundation year.